I'm Gilad, and I'm part of the UCF Consortium, which is the consortium that hosts multiple open source development projects, and Ucx is one of them. So I'm gonna open the tutorial with giving you a little bit of information about UCF, the consortium, the members, what we're doing there. And then after that, I think the team will actually go in and discuss Ucx in more details. So first, the UCF, or Unified Communication Framework Consortium, was established to drive, endorse, and create collaborations between the industries, the government labs, universities, to create communication frameworks and open standard for high-performance data centers that host everything from scientific applications to deep learning, machine learning, and so forth. The consortium hosts actually several projects. Ucx is one of them, Unified Communication X, that I think it actually was the first one. And beyond that, there are several others that I'm just going to mention now. I'll give you a little bit about those, some information about those projects. There is Spark Ucx, which is an open source code. Obviously, everything is open source. Open source code for enabling Ucx for Spark. OpenSnappy, or Open Smart Network API. It's a project to create open source and standard way to access computing on the networks, or computing on DPUs or IPUs and so forth. UCC, it's actually the sister project or the brother project of Ucx. If Ucx is aiming or focusing on point-to-point communication, UCC, it's actually adding collective communication. So working together with Ucx. UCD, it's a project that started by the Oregon National Lab to look into advanced data type engines, as well as we have an effort on creating a new set of benchmark, or a new benchmark suite called HPCA, where the motivation of that benchmark suite is to enable ability to measure the compute power or the computing capability that exists on the network. There are several board members or founding members of the UCF consortium. I'm happy to be part of a great team, and we meet once a month. We'll review the progress of the projects, giving guidance for the futures and so forth. Next one, Oscar, please. So Ucx started multiple years ago from a few people that sitting around the desk and trying to create a new, thin, effective framework or communication framework that can be used to connect the higher level frameworks or the applications to different kind of networking hardware on the other side. Obviously, there were multiple frameworks out there, but each one of them were actually focusing on a different kind of hardware and bringing different kind of things. And the motivation was to try and merge as much as we can together and actually come with a framework that can provide the high performance, will be thin, not that complicated, and can support a broad range of architectures and systems, all the way from even edge devices, as we call them today, into large supercomputers on the other side. And we had thought about the possibility that instead of creating something which we can unify multiple framework, we'll just create another one, but we try not to do that and actually replace multiple frameworks with one. So that's kind of the early days of Ucx. Next one, next slide, please, Oscar. And at that point, we start to migrate multiple things that were there at the time. So there was the MXM, which was an effort that was managed by Mellanox at that time before being acquired by NVIDIA. PAMI from IBM, UCCS from Oak Ridge, and so forth. And we actually took the good part from all of those frameworks and combined them together into Ucx. And Ucx was aiming on performance, on portability, so you can use it on a small system, you can use it on large systems, variety of infrastructures, and so forth. So that was the motivation, and the rest is history, actually. Next one, Oscar. So the motivation with Ucx is to be able to support all of the higher level frameworks, and not just to provide capabilities for MPI or Mpigas and so forth, but also looking for analytics and databases and storage and other things. So to make it as portable as possible, supporting any sort of computing engine, if it's an x86 or a Power CPU or ARM or GPUs to their different kinds, or DPUs or IPUs or smart NICs, and to be able to bring a high performance universal data mover framework in that sense. Next one, Oscar, please. So we build the architecture, and I think the architecture will be discussed later today in much more detail. So I'm not going to go too much here, but as you can see here, we brought support for Rdma, for all of the Rdma elements in that sense. Rdma networks, if that's InfiniBand or Rocky or iWarp, different kind of GPU and accelerators. There is 2 examples here, which include NVIDIA and AMD, but obviously it's not limited to that. And then also for other networking architectures, which could be a proprietary class of architectures or non-RDMA or shared memory and so forth. So essentially supporting everything that exists and providing actually the ability to support new architectures as they will be introduced to the market in the future. Next one, please. Thanks, Oscar. And this is example of portability. So what we build actually can run on Raspberry Pi, can run completely on what was called smart NICs, and now it's called IPUs or DPUs, and all the way to clusters, large clusters, and the biggest supercomputers out there. There are tuning for the different CPU architectures, if the x86, the variations, the ARM coming from different kind of companies, if it's Fujitsu or Huawei or others and so forth. So again, I mentioned that before, but motivation was to support from small components, from edge components, all the way to the large systems, all the variety of computing engines, all the variety of networking architectures. Next one, Oscar, please.
Excuse me, how we can get the slides of this tutorial?
How you will be able to get the slides of this tutorial? Yeah. I'm sure that we will definitely post, by the way, the slides on the UCF website.
UCS? What is the UCF?
UCF website. I'll put the link. I'll put the link in the chat in a few minutes. By the way, on the website you can also see the presentation that were done in other conferences. By the way, so there is a good set of presentations and data. But the slides will be posted.
Sure. But what is the link for the UCX?
I'm going to put in the chat.
Yeah. Thank you.
Yeah. And we have a slide that talks about where the slides are also going to be available. So
yeah, that is also there. But I'm going to also put the link. Yeah.
Absolutely.
Yeah. And from user perspective, it's good that it's good to see the great adoption, by the way, of Ucx. if you're looking on Ucx. I'd say that probably every month we're kind of learning about new models that are using UCF, or new solutions or new architectures that are using UCF. So it's great actually to see the expansion of UCF and see how it's being used almost everywhere. So all major MPI libraries actually include UCX inside, or portions of UCX inside, if that's MPH or OpenMPI. The NVIDIA library, the Huawei library, the Intel MPI library, OpenMpi, PGAth, Charm++. Charm++ runs actually directly on Ucx. So if we have some application that runs on top of MPI, and then MPI runs on top of Ucx, in that sense, there are also libraries that actually run completely on Ucx, and Charm++ is one example, which means that NAMD can also run directly on Ucx. Rapids, Dask, NVIDIA Nickel libraries utilizing Ucx, and so forth. So just a few examples on the broad usage of Ucx today. Next slide, Oscar, please. And we love testing. We want to make sure that every release is robust, is reliable. So we do put a lot of focus about that. There are multiple systems that are being used. Actually, time on those systems being donated by different companies and organizations. And we're running a lot of tests per commit for every release that we're doing, kind of aiming between 2 and 3 releases a year. Next slide, Oscar, please. 2 years ago, we were honored to be awarded. So Ucx received the 2019 R&D 100 award for the achievements, for the usage, for the creation. So you can see a picture of some of the folks that participated in the 2019 user conference, happened in December of 2019. We did a conference, by the way, last year, December of last year, but that was virtual. And we do plan also to do a user conference in December this year, which probably also going to be a virtual one. Next slide, Oscar, please. So those are useful links, by the way. So website of Ucx, it's openucx.com, and there is also a link to the GitHub and to join the mailing list. Ucx is part of UCF, and I'm going to put the link of UCF on the chat box, and on the UCF website, you will see also the presentation being done before. So I'm going to put the link on the chat, so you don't need to copy that. You can find the other resources, obviously the documentations, where to download the code, how to join the mailing list, and so forth. I think that was my last slide.
Yes. So, yes. So thank you, Gilad, and we really appreciated your introduction. And we're gonna start the tutorial. This is a tutorial that we put together with very different people from the community that are users of Ucx and also part of the UCF Foundation and organization. So we should basically want to say special thanks to Jeff Chung from Georgia Tech, Josie Itijin and from NVIDIA, and Matt Baker from Oak Ridge National Laboratory, who helped us to put together the tutorial. This tutorial was also, we have a lot of material also from other contributors that are not presenters, but we have a lot of material, and this is the most up-to-date tutorial that we have for Ucx. And with that, I would like to introduce the next speaker, who's going to be Jeff Chung, who's going to give us a little bit of an overview of and the first part of the tutorial. I'm going to ask Jeff to share his screen so that he can start driving the slides.
Okay, thank you, Oscar. Yeah, and just to point everybody, if you look in the chat here, we have a repo for this tutorial, and also Glad has posted the links for the UCF Consortium organization. So we'll make sure that the slides and link to the examples is kind of replicated in both places. Okay, so thank you to Glad and to Oscar. I just want to point out that, we have different expertise here. Obviously, Glad pointed out that his involvement with Ucx and the UCF Consortium. I helped run a novel architecture testbed at Georgia Tech. One focus of that is smart networking. So I'm kind of new to this space, but like a lot of you, learning more every day. Then we have folks like Yassi and Matthew, who are kind of experts. They spend a lot of time actually implementing things with Ucx. So I'll provide some initial overview, and then if you have very tough questions, I may kind of bring them in and ask them to help dig into some of the details. So again, just to remind you, we don't have all the links here. We'll kind of repeat some of the things, but there's the Ucx mailing list for this specific tutorial. Right now we have kind of a GitHub repo. You can go and check this out. It's also in the chat here. There's the main Ucx read the docs, and then there is a Slack channel for how to interconnect. I think we're all on that. While we're presenting, we may not track it too closely, but somebody should be on there. So if you have questions that you can't get answered here, feel free to post there. Okay, so to go over the agenda, like I provided the overview here of kind of the ecosystem, sort of how we went from Ucx to this wider UCF foundation. It includes other things like OpenSnappy and HPCA. This part of the tutorial we're calling the Ucx Basics. We'll go over a little bit more motivation of how do we get to this point of creating this Ucx framework. We'll talk specifically about one piece of it, which is called Ucp, and then we'll go into a few kind of demos. At least two of these demos are in the repo that I pointed to. You can technically pull those now and run them. There is one that we didn't totally finish. It's the Python binding one that should be updated in the near future. And then kind of the later part of the tutorial, we'll talk a little bit about some of the Python Go Java bindings, and also how you actually use Ucx to implement something like Openmpi and OpenShmem. So feel free to ask questions as we go, either in the chat or by speaking. Okay, so we'll step back a little bit and we'll say, why, what are we really worried about with Ucx? Obviously, Glad mentioned that you can run this on a wide variety of devices, so you can potentially use Ucx as kind of a communication middleware for like a Jetson or Raspberry Pi device. But the initial motivation is really focused on kind of supercomputing and things related to petascale and exascale computing. So that's why we said here, we're mostly going to be talking about something that is kind of at the larger scale, but obviously you can deploy Ucx in a lot of different places. As an example, if you think about kind of the traditional TCP IP stack and something that is more of a HPC type of architecture for networking, they have sort of similar layers, but what you'll notice on the left-hand side is that you have kind of your application through your network are typically software and OS layer capabilities. Then, depending on the device, you'll have either a software or hardware data link, and then of course a hardware physical link. On the right-hand side, we have kind of the corollary for something like InfiniBand. Note that a lot of accelerated interconnects have similar frameworks. So this is obviously we're probably more familiar with InfiniBand for most of us, but this also carries over a lot of HPC interconnects. But the key thing to note here is that many of these layers are actually implemented and accelerated in hardware. So this provides performance benefits, especially when you're thinking about HPC. It provides lower latency and capability for higher bandwidth. But it also means that it's it's implemented and needs to be supported slightly different ways. So what are some key concepts to think about? There are two different ways that you can kind of send data. One is this sort of send and receive type model, where you have either a blocking or non-blocking kind of buffered send between two devices. You also can have what's called one-sided communication. So this is something like, if you think about a put or a write operation, or a get or read operation, and then associated atomics that kind of built on those. There's also this concept of rendezvous. So rendezvous is basically when you're trying to set up something like a one-sided or an RDMA type communication. Typically, you need to initialize that in some way. So you need to set up some kind of memory region. You need to exchange some metadata to be able to connect two different endpoints. And then you actually need to do the data transfer. Then there are a few other things that you typically encounter in HPC interconnects, like OS bypass, and then of course transport offload. Basically moving some of the capabilities of your RDMA or data transfer into the hardware. So just to review, if we say OS bypass, really we're talking about two different scenarios. So there's something that might be like a legacy sort of non-RDMA type transfer, and on the left-hand side we're showing an instance of that. In that case, you're doing an initialization, a query, then you're doing some kind of send receive operation, and you're interacting with the operating system and with the driver on most of these send receive type operations. On the right-hand side, it takes a little bit more effort to do the initialization. So you have to set up all that metadata, and you have to do that rendezvous protocol between your two endpoints. But once you do that, you can kind of avoid going back and interacting with all those OS layers to transfer data. So the goal here is we want to kind of set up some kind of multi-node endpoint, and then be able to efficiently move data between those two endpoints. When we think about different types of RDMA communication, there are two different types that you can use, and this is something that we won't dig super deep into with Ucx, but underneath some of the higher level APIs at the lower level, it actually can decide, okay, do I want to do what's called a zero copy? Basically, do I want to copy directly from one source buffer to a destination buffer on a remote node? This tends to be very good if you have very large messages. Or you might say, okay, I want to copy a small amount of data into a temporary buffer, and then be able to use that for either a send or receive or put get type operation. There are different trade-offs for using each of these. Typically, when you're using a buffered copy, that means that you can kind of reuse the buffer, so you can you're allocating more memory, but you're also potentially reducing latency because you're not blocking all this source or destination memory region. So just an example of what we mean by zero copy. On the left-hand side here, you see if we said, okay, if we're not doing any kind of buffered or DMA type access, we both might copy data multiple times into several temporary buffers. And if we're doing an operation that is like a traditional TCP/IP, then we're kind of hitting multiple layers of our software stack. Whereas if you remember in our OS bypass slide, we set up this DMA connection with zero copy. We're actually saying, okay, I'm not creating any temporary buffers. I'm just going to move my data, from the source to the NIC, remote NIC, and then to the destination buffer. Of course, then, as we mentioned, if you want to do something else with this data buffer, you have to wait until this operation is completed, or you risk, messing with the consistency of your data. All right. So we talked a little bit about RDMA read and write. There are different atomic operations that you can do on a remote memory. Ucx supports many of these operations. And as we'll talk about, it does this across different hardware implementations. Things like swap, compare and swap, add and XOR. So sort of simple operations on remote memory. And then also provides support for kind of higher level group communication directives, like reduce, all reduce, and all to all.
Yep. And that's part of that's part of the sister project, UCC.
Mm-hmm. Right. So we won't talk a lot about this today, but there's another project that is called UCC that is not publicly released, but that's actually to provide an optimized version of these directives. So hopefully a future version of this tutorial will have a little bit more detail on that. Okay, we talked about RDMA. We talked about where some of the different types of RDMA and different operations. Now we want to revisit and say, okay, we have this RDMA operation. This already improves our communication a little bit for HPC software. Then we want to think about, okay, what are the other bottlenecks that we need to focus on? Obviously, we have things like our transport and our physical layer. So on the right-hand side of this figure here, we have our network drivers. So if those are software, that's something we have to interact with, and it has associated latency for doing control and data operations. Then we also just have the physical latency of interacting with our hardware. Obviously, it's tough to minimize the network hardware latency without actually changing the design of the hardware. But then in the middle between sort of our low-level physical devices and our software, we have what we're calling communications middleware. And there's been several different implementations of this, things like GasNet, Glad mentioned, MXM, UCCS, one-sided models like ARMC. And some of these are sort of research-oriented, some of them are vendor-oriented. But this can be another source of performance bottleneck that we'd like to improve. So just as an example, if we're trying to optimize, the latency for, say, an RMA put operation in a kind of traditional implementation, we might have something like a standard vendor-provided Open Fabrics driver that might be anywhere from 100 to a few hundred nanoseconds, and then we have kind of this vague amorphous piece, the communication middleware. And for something like OpenMPI or Mbapich or OpenSHMIM, that middleware can kind of differ depending on who originally implemented that programming language. So the goal is on the right-hand side here to take something like Ucx, kind of optimize that latency path, and then also provide some standardized API. So just to remind you, there are a lot of different network programming interfaces. We won't go into a lot of these here because a lot of these are research-oriented. Some of them are vendor-specific. Things like, again, we mentioned UCCS from Oak Ridge, kind of fed into the development of Ucx. Obviously, there's a lot of low-level APIs like InfiniBand verbs, and then there's vendor-specific, interfaces like MXM, PAMI, and many others. So this is just to say there's a lot of different interfaces you could use. And the benefit of these different types of APIs, we'll kind of go through all of these to kind of see, okay, what are the benefits and disadvantages? Something like a vendor-specific API, that it's going to be very well supported typically. It will be optimized for performance, specifically with the hardware that that vendor provides. And the code is typically production grade, as opposed to, sometimes open source software can also be production grade, but depending on how big the project is, it may have a few more bugs. Obviously, the disadvantages are that it's specific to one piece of hardware, and it doesn't really have any flexibility if you're trying to incorporate it into like a heterogeneous cluster system. On the other hand, we have open source APIs. These tend to have, for the most successful ones, they tend to have good user communities. They tend to be easy to pick up. Obviously they have a GitHub repo. They're good to do research on. But at the same time, if they don't really have buy-in from a specific vendor or hardware implementer, then they may not be as optimized. So a very simple example is if you think about kind of a vendor-specific compiler, and then if you look at something like GCC, which is a very successful open source project, GCC is a great compiler, but it's not always as optimized as some of the other tools, and that's just because it's tough to develop this as part of an open source ecosystem. And then finally, we have things like we mentioned, say, portals as one example. Research API is really cutting edge, provides kind of the latest features and is very, innovative in terms of, being far ahead of what vendors might provide. So this is a good place to kind of experiment and see what is sort of next in terms of implementing, support for different devices. But then, of course, the big con is that support is kind of limited to the research team that's developing it. So you really need to have buy-in from a larger community and or a vendor to get these to be well supported. All right, so we went through these three different kinds of interfaces and middlewares, and as you might expect, we really want to be somewhere in the middle of that Venn diagram. We want to have something that has vendor support, that's optimized for different types of hardware, that has a growing and vibrant community, and it also allows for incorporating some of these innovative, and forward-looking features. So, as you might have guessed, you're in the Ucx tutorial. That's Ucx is meant to sit at the middle of this Venn diagram. So, we're revisiting a little bit of introduction here again, going a little bit more detail. But, we talked about, what are the issues with trying to implement this kind of middleware. Ucx is trying to bring together this idea of an open source community, vendor support, so collaboration with industry partners, laboratories, especially in the US, and academic institutions. And ideally, we'd like to generate something that's both open source and production grade. And there are a couple different features that were sort of designed as the key points that had to be met for this to be successful. So that is, common API, production grade, optimized for many different types of platforms. So performance not just on one platform, but across platforms, and the ability to be extended by the community. So this slide obviously will change over time. Mellanox and NVIDIA are sort of merged now, but I think Mellanox has contributed a lot of the initial sort of high performance and optimized Rdma implementations, especially for transport and kind of hardware protocols. And so a lot of their expertise sort of went into some of the hardware optimization support. We mentioned UCCS from Oak Ridge. Other research labs like Flannel help design network APIs. They're working on things like OpenStappy. ARM has also contributed to this general network API. Obviously, they'd be interested to support this with kind of the growing ARM ecosystem. NVIDIA, and of course now merged with Mellanox, is interested to see low latency, communication support for GPUs, both via something like InfiniBand and also via NVLink. And IBM contributed via PAMI. And then of course you have these academic institutions, which might be a little bit smaller, but they provide some of this forward-looking and innovative research that feeds back into some of these other pieces of a collaborative middleware. So we're reiterating, but what's important to know about Ucx? Hopefully it's simple to use. We'll talk about Ucp and the API you can interact with in kind of a simple fashion. It's consistent. It should be performance portable across a lot of different network infrastructure. And then it if capabilities that you can kind of extend it. So we won't talk a lot about the low-level API, which is called UCT. But if you were a hardware designer, you might work with that. If you're an application designer, you'll work more with UCP, which we'll talk about here. And then there are a lot of options just to kind of optimize performance for the type of environment where you're deploying it. This last bullet point here, accelerators are represented as transport. This is kind of a key and novel idea as well. A lot of times when you think about networking, you may not even think about accelerators. They may be part of the node rather than part of the overall data communication scheme. But Ucx is focused on incorporating those kind of first-class citizens. Okay, so hopefully now we've convinced you that Ucx is a good thing. The standardization, and we'll go into sort of the design of this, and we'll talk about some of the APIs in a little bit more detail. There's the high-level API, communication protocol, low-level. There's kind of services, and then a newer memory management API. Okay, so UCP is the high-level API. That's what we'll talk about mostly today. Under the covers, this uses UCP to actually do data transfers, but this is meant to be more geared towards application developers. So this is higher level. In other words, you don't have to worry about should I do a 0 copy or should I do a buffered copy? You basically just say, okay, I want to send some data, and then I'd like for the Ucx middleware to help me figure out the best way to do that. UCT is where you actually can make some of those decisions, where you can say, okay, actually, I need to specify how some higher level function call is going to send data. If you want to do that, then you kind of operate with this low-level API, UCT. This is also used to kind of set up and instantiate these endpoints and the Rdma communication between them. Then there are, of course, service APIs that are used to kind of provide additional setup and debugging support. And then finally, a new feature called UCM, which actually didn't show up in the last tutorial that was done at Hiring Connects. This is relatively recent addition. It's kind of a user addressable API, but this is basically provides an API for memory allocations and deallocations. And as you might expect, if we're thinking about things like accelerators, this becomes much more important because maybe you're thinking about a GPU that has something like unified shared memory, and maybe you need to allocate memory that's accessible from the CPU and the GPU, and then maybe you also want to send data from that memory region to either another GPU within your node or across nodes. So UCM helps you kind of manage some of those abstractions.
This package is similar to DBDK?
My understanding is DBDK is more focused on kind of like storage and I mean it's the data plane. So this is meant a little bit more for kind of like a HPC context than DBDK. Okay, so we're revisiting our figure, and we kind of filled in the pieces. The high-level API Ucp, provides a lot of functionality where you select your specific transport. So, for instance, am I doing Ethernet, InfiniBand, NVLink, or something else? Multi-rail, multi-device support. Am I doing RMA? Am I doing active messages or tag matching? And then also kind of, setting up the initial connection. And then again, UCT focuses on sort of the lower level interface to devices. You'll see here, CUDA, ROCm, gray areas interconnects, and then things like traditional InfiniBand and TCP/IP. All right, just to reiterate, Ucx is a communication middleware framework. So it doesn't replace your device driver. You still have to have vendor-specific device drivers, but it's meant to be low latency, and also I think with a lot of vendor feedback and interoperability, then ideally it's a very low latency framework that sits on top of these drivers. Okay. Any questions or any other questions before I dive into UCP?
So I just want to add that the UCM memory component also focus on the events notifications for the allocate and deallocate across the different devices and accelerators, and that's another part for that part. Mm-hmm. The question came up.
Okay, great, thank you. Okay, so we're going to talk a little bit about UCP today. UCT will kind of leave as an exercise for the reader. Obviously, if you have questions about that, that means you're doing some low-level interaction with network hardware. So kind of an introductory tutorial like that, we'll kind of skip over that. That in mind, we're kind of taking from the quote attributed to Leonardo da Vinci, simplicity is the ultimate sophistication. So the idea for UCP is to make it as simple as possible for users to interact with. All right, so just to reiterate, this is the protocol layer. The idea here is that this will kind of help you as a user, sort of select and set up certain things that will help your application to run at its best performance, and will also help you in terms of doing some optimizations. One of the key things is if you have multiple networks, it should be able to help you pick the best transport for your application. It should be able to help you do data transfers without having to worry about, do I do those zero copy or buffer messages? Do I do intelligent fragmentation? Basically, do I take a large message and break it down into smaller pieces, to optimize for the average latency of those messages versus the bandwidth? If I have a multi-rail, that is a system with more than one NIC, how do I split data across those to get the best performance? Ucx is meant to help you sort of decide that, without needing to specifically specify that at the UCP level. And the key thing is that, it's meant to be able to handle a lot of corner cases, whereas if you try to implement this, say with InfiniBand verbs, you would have to worry about a lot of these specific issues in terms of, okay, how do I fragment my data? How do I buffer it? Obviously, you can get high performance communication there, but it's a little bit more difficult to program. We're going to talk about UCP objects, and we'll kind of go through these several different times. So, hopefully, this will not be the only time we see it, but there are a couple different objects that you need to set up a connection between two endpoints. When we say an endpoint, basically we mean a remote piece of memory and a local piece of memory. Is actually like a memory structure, but then an endpoint kind of gives you a pointer to initiate some transfer between two buffers within a memory region. So when we say an endpoint, we're saying like a distinct buffer that may be part of a larger memory region. But there are a couple key objects that we'll go into more detail. One is Ucp Context. That's kind of the global context for the application. A good way to think about this is, for some reason, if you were running two different types of applications, maybe you're running an MPI application and a SMIM application, each of them will kind of allocate data differently, and it'll have sort of a different context in terms of how it does Rdma accesses. Then we have workers, which are kind of basically how do you make progress in terms of sending and receiving data. A lot of times a worker might be matched to like a thread, or in the case of MPI, to an MPI process. Talk a little bit more about that. And then again, an endpoint kind of represents a connection between one of these local and remote communication threads. So you have to have an endpoint to send data within Ucx. Okay. Gonna admit a few people here. Okay, so here's kind of a high-level diagram on one side, basically one node. We have the context. Typically, there's one instance per application process. So I mentioned, say if you have two different applications, they each will have their own Ucp context. Then a context can have multiple workers, can have multiple threads, and then each worker can have multiple endpoints. So, basically, if I'm exchanging data between different buffers on different nodes, each of those is an endpoint that's connected to a local and a remote worker. Some more objects, and then we'll kind of bring all these together. You have kind of this idea of registered memory, so you have to allocate and register memory with the Ucx middleware. This is referred to as the Ucp min object. This is kind of an opaque handle that you operate on. Then in order to do either send, receive, or put get operations on that memory, there's something called the Ucp R key, which is a remote key. And this is used to communicate between two different endpoints. Finally, we have kind of a high-level configuration file, and this is just used to set up the context for each application process. All right, we've expanded our view here. We took that previous picture. Again, we have the context. You can see here, if we want to set up the context, maybe we have a config object that specifies, okay, I want to have a consistent context each time I start this application. I'm going to store all that in this data structure, Ucp config. And then from that context, we might register some memory. We might register like a memory region and then operate on that. Again, we have the workers, multiple workers. And what we've added here is that you see each of these endpoints has, potentially multiple R keys. And this is just, indicating that you might have data transfers to kind of different buffers within an endpoint. Okay. So we'll go into some of the functions, and then we'll kind of bring it back to sort of a two-node example and then we'll take that into the demo. First up, we have something like Ucp init. This is the initialization function. This is basically where you're creating your initial configuration. As we mentioned here, you can pass this config object. This has sort of your parameters. It says, okay, what does my context actually look like? And then what you get out is an initialized pointer to a Ucp application context. Basically this is sort of your first step in any UCP program. You're going to do your initialization to set up your context, and then it's gonna basically do discovery to say, okay, these are the transports that I recognize and that I can use. So, if you think about a standard InfiniBand type system, it'll probably say, okay, I have Ethernet plus TCP, and then I have InfiniBand, with some kind of Rdma type interface. Once you've created that context, then you can start to create workers. Ucp Worker Create takes the context handle. Then you can specify something called thread mode. This is a data structure that says, okay, do I want to do something that's multi-threaded? Do I want to have multiple threads per node? Or do I want to have a single thread that is, that basically has no locks? There might be different contexts when you want to do each of those. I think as Yasi will talk about a little bit later, with MPI, typically you might say, okay, I want a single thread and I want it to be non-locking, just because that makes more sense if you're doing MPI with a bunch of GPUs or accelerators. And then what you get out is a pointer to a Ucp worker type object. And here at the bottom, we won't talk too much about a lot of these, but if you're looking at this later, keep track of the related routines. You can go and look at these in the UCC spec. Obviously, as you might expect, you have something like a destroy routine, get address to the pointer, but then you also have these worker progress functions. So basically, where is the worker in terms of making progress in terms of communication, and then you have things for non-blocking type operations. So fence and flush are specifically meant for, say, if you do like an RMA operation that doesn't, return any status, then you might need to do either a fence or a flush to make sure that actually completed. All right. We mentioned at the bottom of that last slide, we have Ucp Worker Get Address. That is, passes us a kind of a pointer to that address. Then you can use that address to send to the remote node and basically connect those two workers. So if you remember, we mentioned that you have to connect endpoints, and endpoints represent a connection between two addresses. So here we're getting an address for Ucp worker, and we're going to send that sort of out of band as part of our initialization to connect two workers, and then to set up endpoints between those workers. So once we've gotten that address, and let's say we've sent that to our remote node, then we can go ahead and we can create our endpoints. Here you'll notice that we have handle to the worker, and then you have this destination address. So this is kind of your local pointer to your Ucp worker, and then you need the remote pointer to your destination address. So send this sort of out of band. Ucp will help you kind of set this up between two different nodes, but you might imagine this would be some kind of tag send receive between the two nodes to exchange these worker addresses. Then once you've done this, then you can set up multiple endpoints, and endpoints can refer to memory buffers that you can do data transfers between. The key thing to note here, each endpoint can be associated with only one worker. So you can't share an endpoint between workers. Okay. So we know this is kind of abstract, so we try to draw a figure to put this in, a little more visually. I mentioned there's some out-of-band address exchange that typically happens, via some Ucx client server or something like a tag send receive over TCP/IP. But we have four nodes. We're calling entity A through D. Entity A, creates a context. So does B, C, and D. A will create a worker, and then you'll get an address from this worker, share it with these different entities where they've all created workers. So basically this we use get address here, send it to B, and then B can set up its own worker, and you use that to create an endpoint between A and B. And then we do this multiple times to set up endpoints between entity A and all the other nodes. Okay. So if we wanted to do something like a hello world or a simple kind of server send receive, what we might do initially is we'll say, okay, we'll create an application context. Then we'll create that local worker object. We'll get the address for that and send that out of band as part of this bootstrap type phase. And then, the remote node will also create a local worker object. It'll take that remote address that you sent it out of band, use that to create its local endpoint, and then connect that to the remote endpoint. And then you can actually proceed to doing your communication. And, of course, then you disconnect at the end.
Hey, Jeff, can I ask a question real quick?
Mm-hmm.
Kind of on just to clarify the endpoint worker scaling, going back a few slides where you had that picture.
Mm-hmm.
Yeah, there.
Right.
So is each, assuming like an entity is a node or something, is each entity creating a unique endpoint worker pair for every, is every pair of entities have to create unique endpoint pairs there, or how many endpoints do you have for some number of entities?
Right. Yeah. So each entity has to have a local and remote worker pair, and then you can technically do multiple endpoints per worker. So entity A and B, you need at least one worker connected to on each of those, and then you might have multiple endpoints that live underneath that worker. So as you see here, you don't necessarily have a ton of workers, but you do potentially have a large number of endpoints, because an endpoint is unique for each node or entity, and then also for each kind of memory buffer that you're connecting.
Okay, thanks.
Yep. And I don't know if I can speak to the scalability, because I haven't tried this at scale. Obviously, I tried it, 2-node, but my understanding and assumption is that it should be reasonably scalable up to a large system size.
Mm-hmm. Yep. Yeah, Yossi can comment on that a little bit. He's one of the designers. But and maybe in the MPI section, we can talk about that a little bit more.
Yep. So I don't know if anyone has questions. Technically, we've reached our first break. I know this is kind of cliffhanger. When we come back, we'll kind of talk about the Hello World demo, and then we'll talk a little bit about Ucx memory management. But I think right now we're scheduled to have kind of a 10-minute break. So we'll do that now. If anybody has questions, it's also a good time to ask questions.
Hi. So about the previous question about the scalability and endpoints. So usually, for simple single-threaded applications, you would have only one worker, and that one worker can connect to many other workers, many other remote workers, and each such connection will be represented as an endpoint. And usually an endpoint is something which is pretty small, obviously depending on the transport, but if the transport is scalable, then it should be a really small memory footprint to create an additional endpoint.
Great.
This is with Shaman talking. What's an endpoint address look like? Is it like a logical network ID and something else?
So actually there are two endpoints. When you create an endpoint, you would have the protocol level endpoint, which is essentially pointing to some configuration which can be shared between endpoints of the same type. and it used to know how can we select protocols, what is the transport configuration for that endpoint, and so on. And there's also the transport level endpoints, because for every UCP endpoint could have multiple such transport endpoints. For example, if we have multiple devices, multiple lanes, if, for example, between processes on the same machine, we might want to communicate both using RDMA and shared memory, or different kinds of shared memory. And then we have multiple transport endpoints, but usually if you connect to a different machine, there would be less transport endpoints, because less transports are usable in that mode. And the transport endpoint is the one which actually holds the address vector. In case of InfiniBand, for example, if it's one InfiniBand subnet, it would be just a remote lead and remote QP number, or remote DCT number, depending on the exact transport. If it's a Rocky or InfiniBand cross subnet, it will also contain a global routing address. In case of TCP, it's actually the socket file descriptor. In case of shared memory, it would be the address of the remote memory to which we attached, and using it as some kind of shared FIFO to post active messages. So it really depends on the transport.
Okay, cool. So that makes total sense now. It's abstracted away, obviously. Yeah, cool. Thank you.
Sure.
Okay, great. So yeah, I guess we'll take a short break. You know, if you have questions, feel free to post them in the chat or ask. Then we'll kind of restart back in a couple minutes. Okay, we'll start back here shortly. So we talked about some of the Ucx basics. We talked about some of the UCP setup. I think now we're going to do a little bit of code walkthrough with Matt. So as we mentioned, you know, in the chat, we have this repo for the tutorial. You know, eventually that'll be hosted with the UCF as well. But yeah, it has two examples that are kind of fully complete. I will be walking through those today. Obviously, you can download and run these. You know, we didn't want to have people try to spend too much time trying to build and install stuff. So we'll kind of walk through and talk through them today. But those are also available for you to pick up and to test out. And if you find bugs, to do PRs on. So let's see. So Matt, are you ready to do
yeah.
Do the walkthrough? Yep.
Mm-hmm. All right, give me a moment to share my screen.
Okay.
Okay. And just getting my bearings in this Zoom thing. Okay, so this is the repository that Jeff has linked in the chat with slides and example code. So for example, these slides will be in the slides directory in PDF form. So code that I will be showing you is this Ucx Hello World set up so that once you have Ucx installed, you just do a make, and that will, and all you have to do is set up the path where you installed Ucx into, and then just have to do a make, which then builds your code. So first I'll run the code so that you can see where this example is going. And then I'll show you the C source. So this is set up to run in a client server mode where you have a server application that will print out the Ucx configuration that it will be using. and then listen on a TCP IP port for a connection. That TCP IP port is the out-of-band mechanism that will be used to exchange Ucx addresses. On this particular machine, that address will be 231 bytes long. So from there, you tell a client that a server is listening on the local host, and then it will send its own address to that, get back this test message, and then both will clean up and exit. So since Jeff has just gone over the setup and initialization, the code I will go over is in the main function, where this will be a practical example of how Ucx actually gets stood up and torn down. So as you can see, we just set up our C declarations and initializations, check arguments, and then we immediately jump into Ucx code, starting with config read. When I ran this example, this is where it read in all the configuration parameters, both the ones built in and the ones set in the environment, and set up a configuration structure. This is done so that before you initialize the Ucx library, your application can adjust what parameters get set so that you can optimize this particular instance of Ucx to be optimized to your application. So after checking status, you then see the parameters field. So this is the Ucp parameter structure, and in all the Ucx structures for these sorts of configurations, they will all have this field mask. This is done for compatibility so that future libraries can add new fields to this structure, and applications built against the older header files can still run on with the newer library, where it will understand what parameters the user is going to be setting and expects the library to respect. And then if you have an application that needs a newer version of Ucx and you try and build against an older library, that older library will be able to understand that the user is asking for fields and features that this library doesn't understand and fail gracefully. So for the application context, in this demo, we are asking for the tag matching feature so that we can get tag sync, tag receive like you would have in an MPI library. And then this represents the request, the size of the user's request field, where the user's application will implement the request logic, along with passing in a initializer function that gets run on the Ucx managed request on a first allocation. And so after setting all that up, this is the part where your Ucx application gets initialized. So for example, if you were implementing an MPI with Ucx, this is what gets called in MPI init to actually stand up your application context and get ready to exchange endpoint information. So this will just print out the configuration used. This is where the screen dump happened for all the configuration parameters. Normally not used in typical applications, but it's good for an example so that people can see what kind of tunables are available. After that, you give back the memory, check status, and now we're ready to stand up the worker. As Jeff explained earlier, the worker is the part that's actually driving the hardware. And so we will be setting up one workers for our communications. And again, we see the familiar field mask model, where the worker parameters is being told that we will inform it of what kind of thread mode we would like, and then tell the UCP worker that we will be running in single threaded mode so that we do not have to take any locks inside of the library. After that, you pass in the configuration parameters and the application context, and we get back a worker structure. Now, at this point, the worker is up and operating and ready to receive traffic. Okay, so check status. And then here's the part where in our demo, it prints out the size of the address. Memory serves, we had an address size of 231 bytes. And here's where it starts the out-of-band connection. This is because the server and the client need to exchange addresses. And so here we're just doing that with simple TCP/IP sockets using the good old Berkeley API. It's hidden away in these helper functions, but if you've worked with TCP/IP sockets, you already know exactly how this goes. So this is for the client code path, where when I was running the example earlier, it was told to look to localhost. And so it looks to the local host, and this is where it receives the server's address data. And then after a return value check, it gets its size, it allocates the data to actually receive the 231 byte structure, and then it receives the server address. Now here's the other end of that, where the server listens on its port that's hard coded up above, and then after it receives the connection, it sends its the size of the address so that the client knows how much data to malloc, and then actually sends the address. From there, it runs the test. Now, we will go over how run test is implemented to unpack the endpoint and start sending traffic across these endpoints in part 2 of this tutorial. Now, from there, yes, Oscar?
Yes, so we wanted to clarify that when we say we're sending addresses, we're basically exchanging the address of the worker objects. From
yes, although the way that this works, the server sends its address to the client, and then the client stands up an endpoint to send its address to the server, so that we get the endpoint pair between client and server, and then after that, the socket's no longer needed.
Correct.
So it comes up again where we implement a simple barrier using the TCP/IP socket. Now, for example, HPC workloads, instead of using TCP/IP sockets, you would use something like PMI. But since this is intended to be a standalone example, we used good old TCP/IP instead. And then after that is the cleanup code. Close the socket, free the memory from the address, and then here we start releasing Ucx data types. Now, the endpoint will get cleaned up in the run test. So here we go in the opposite direction that we instantiated these objects, cleaning up the worker, cleaning up the worker's address, destroying the worker, and then tearing down the application context before exiting the code. And so with that is part one of our code review. In part two, we'll stand up the endpoints and do tag send, tag receive to move data between host DRAM. Anybody have any?
Yeah.
Yes.
Going back to the threading that you were covering real quick, can you just elaborate a little bit about how that corresponds to MPI threading or the device threading models?
So this is meant to map pretty closely to what MPI, the MPI spec will expect. Yossi can correct me if I'm wrong on this, but I think that the main model that Ucx works on is that you have the single thread mode, which does no locking. Then you have a multi-thread mode where there is locking inside of the library.
Yes, that is right. So there are three main important modes. One is single, where you guarantee that all calls to Ucx would be from the same thread. Another is serialized, which means they can be from different threads, but they cannot happen at the same time. There are some cases related to hardware register flash, which would be different in this versus single mode. And there is multi-thread mode where Ucx would have its own lock. Currently, it's a global lock on the worker, so that multiple threads can access the same worker. And usually, I mean, applications which use multiple threads could benefit from creating multiple workers. Each of them would be single, so they would not contend with each other. And this way, the message rate and bandwidth could be better with multiple threads. But it's not done today with OpenMPI because the matching queue has to be global.
Okay, thank you.
Any other questions?
Sounds like not. So Jeff, would you like to take control back?
Yep. Thank you, Matt. So yeah, so we're going to come back and revisit this a little bit. But first, we're going to go through some of the data transfer types,
yep,
and then also the memory model here.
Yeah.
So let me.
Yes. So yes, so to put everything together, yes. So basically, what Matt demonstrated was the first part of the Hello World example, where we are demonstrating how an application can create a context, it basically what is needed to do that, and we show basically the configuration and the parameters that are needed to do that. And then we show that, yes, the first thing we need to do is definitely to bootstrap to establish those connections. And we used, the example, talk about the TCP/IP way to do the bootstrap, although that's just one option of the many that is possible. And here is where, yes, we are basically, the server is basically sending the addresses of the workers it creates, so that with that information, basically we can create the endpoints. And so we can establish the communication between the different processes between the client and the server. So that's kind of like, the summary of what this is doing. And yeah, there is at a very high level, and that's what you should look like in the example. And with that, if there is any more questions, we can go to the next set of slides.
Okay. As always, feel free to post things in the chat or kind of speak up as we go. This thing will let me sorry, my PowerPoint has decided it wanted to kind of explode. Okay. All right. So we'll revisit that hello world. We'll kind of finish that up. But we did also want to talk about some of the other pieces that were important in order to write applications with Ucp. So there are two concepts that we're going to talk about. One is this idea of memory management. So we mentioned, this Ucp mem object, which is kind of an opaque pointer to a registered memory region. And then also we want to talk a little bit about some of the actual data transfer functions that you would use. So we talked initially about, how do you set up these endpoints? How do you create context and workers? Some of the options for that. Now we're going to talk about how do you allocate memory and how do you use that memory for communication. So first up, we have Ucp memmap. Here again, we're passing the context as we are with a lot of functions. Then we have an address to a pointer, basically to a local memory region, and then we're going to create a Ucp object out of that. As you might expect, you pass the length or the size of that buffer, any kind of flags, and then what you get out is this memh_p handle. Then, as with any type of kind of managed malloc, so if you think about like the CUDA malloc, you also have a related routine to actually unmap and help destroy that buffer. When you have this memory region, we talk about this idea of needing specific R keys to be able to communicate, with different memory buffers for endpoints. So with the memory region, we're gonna create an R key locally. We're gonna pack that into an R key buffer. Again, we're gonna specify, as an input, the context, the memory handle, so the opaque handle to the memory buffer we want to operate on, and then what we're going to get out is this R key buffer object that then we'll hand off to the other node, kind of an out-of-band fashion, and that's how we sort of connect these two memory regions across nodes. On the other side, if you get one of these packed R key buffers, you then have to take that. It might have multiple R keys, that can be used with an endpoint. And so then you actually have to extract each of those individual R key buffer pointers. And so on the other side, you have this function called Ucp. You'll notice it says Ucp underscore endpoint key impact. The other function was Ucp key pack. So it didn't really specify endpoint as an input parameter. Here we're specifying not the local context or the local memory buffer, but we're basically just saying, which endpoint is this key mapped to on a remote node. And so that's the input that we need in order to kind of connect these two memory buffer regions and to be able to do RMA access between them. Again, this has its own kind of related function, Ucp key destroy. Okay, so that's kind of how you initialize memory, then you create an key, you pack it, you send it to a remote node, that remote node unpacks it and associates that with an endpoint. Now we're going to talk a little bit about how you actually do the communication. Here we have two different examples. We have MPI where you can do send receive, either blocking or non-blocking. You can also do one-sided communication with MPI. As we mentioned, put, get, and atomic operations. With something like PGAS type language, you'll typically just have one-sided communication, and there are different functions within Ucp to do each of these. The first one is Ucp put, and you'll see this little phrase that says MBX. That's non-blocking, and I believe that Yossi said that X is kind of an extended version of a previous version of the API. So currently Ucx is kind of the stable is somewhere around 1.10, 1.11, I think was just released. But this Ucp put MBX is reasonably recent. It's in the last 2 API releases, but has changed slightly from previous versions of the API. And just to add different functionality. Here you're taking an endpoint as an input. You're taking a pointer to a local buffer. So you'll notice this is like a raw pointer, specifying that there's some count or length. There is a remote memory address. Remember, we have that associated with the worker. And then importantly, you need to have this R key, a remote memory key, to be able to initiate the RMA through Ucp and Ucx. And then finally, there's some parameters, and we won't really spend too much time talking about those, other than that we might see a few examples of those in the code segments that we walk through. Likewise, if you look at Git, it has pretty similar syntax. Here, this is Ucp get non-blocking X. Again, you have a remote endpoint. You have a pointer to the local buffer, size underscore key count, like a length, your address, your R key, and then your parameters. So if you look at both of these, the syntax is very similar, but remember, this is abstracting a lot of the things that you might do in a very vendor or transport specific way. So you could do this with infinitive verbs, but then that's not portable to different hardware. So this is meant to be generic enough, but also be mapped to something that is high performance by the low-level API. So we talked about put and get. There are also send and receive non-blocking variants. Here again, you have an endpoint, you have a buffer. What's important to note is that you have this Ucp tag structure, and so that's if you're sending kind of tagged buffers between nodes. That's just a way for it to kind of keep track and say, okay, have I received all the data that I need? Again, you have some parameters, and we won't worry too much about those. Receive has a similar context. It does have this additional field here, tag match, excuse me. And this is just a bit mask that is basically used to say, okay, did I get what I expected? So I expected to get, say, at the bottom, these 3 buffers with certain tags, and then I want to check my tag maps to make sure that I actually got those correctly. and I can complete the operation. Remember, again, we're talking about send receive, which is more of a two-sided operation versus put get, which is one-sided. In the case of put get, typically it's not gonna have any notion of did this complete. So typically you have to do a fence or flush to specify that everything should be flushed to memory. Here we're actually matching up and saying, okay, the sender sent what I expected and I received what I expected based on checking all these tags. Just a brief aside, you'll see in all these examples, we have this structure called Ucs Status. As you might expect, normally if you were to do some kind of transfer, you'd say, did this happen? Did this complete correctly? If I did a send, if I get Ucs OK, it was completed. If I get some pointer back with some value, then it failed. Maybe I can do some introspection on that. But otherwise, the operation can be scheduled for send, and you may not have some concept of when is this actually finished. There are some additional request handling functionality that you can add here at the bottom. So you can say, I can specify a request. I can check and see is this completed. I can release it. I can also say, hey, never mind, I didn't really need that data. So a lot of these are kind of specified if you're waiting for data, and then maybe you reach some timeout or some error state where you say, okay, I just need to reset and resend or transition to some different phase of my data transmission. So we had the send and the get variant. Here we have a synchronous version of send, and then also receive. That's kind of the same thing. You'll notice that the parameters are exactly the same, just the semantics of how this is going to operate are different. So in my understanding, the synchronous is basically saying that it's waiting for these to complete before it releases the buffer. And so, you have, a buffer associated with your endpoint in this case that you can't reuse until you complete the send and receive process. All right. Very briefly, we'll talk about atomics. We don't really have any examples of these in our code that I'm aware of, but this might be something that your application may require, especially if you're trying to do some heavily optimized updates to maybe for small messages. Here we have Gcp atomic op non-blocking. You can specify different atomic opcodes. If you remember previously, we said you have things like swap, compare and swap, and XOR. There may be a few other variants, but those are the most common ones that you would run into. You have the buffer that specifies the address of the operand that you're using, and then also a size or count variable. Again, everything else looks pretty much the same. You have this remote address associated with your remote worker, and then the key handle that specifies, okay, this is the memory buffer that I want to update. All right, so we went over how to kind of send and receive stuff. So now we're going to revisit our Hello World demo. We talked about kind of send receive, non-blocking, the synchronous variant, the put get, and how you can use that, and then basically how you wrap up. So I think with that we transition back to our Hello World demo. Matt, you ready to jump back into that?
Certainly.
All right, I will transition off. I don't know if there are any questions while we're switching over, but feel free to speak up. I'll check the chat here.
Yeah, I had another question about the memory allocation routines. The UCP will allocate the memory that you're requesting, right?
Mm-hmm.
How does that interact with, or maybe it's beyond this tutorial, but GPUs and trying to allocate GPU memory versus host memory.
So today it's possible to specify the memory type which we want to allocate. It's yet another parameter to the memory allocation routine. So we can specify to allocate CUDA memory or Roku memory. And then assuming that Ucx has been compiled with the relevant modules and everything is present and initialized, then the memory could be allocated on the right place.
Great, thank you.
Okay.
Yeah.
Any other question? Any other questions? Yeah. No, Matt, it's all yours.
Okay. Da-da-da-da. So part 2, where we go over the send and receive functions and the and sending of data. So the run test function is just an if statement where if it's the client, it runs into run Ucx client. And if it's the server, it runs into run Ucx server, the next function I'm going to go over. So the client starts off creating an endpoint. See the now familiar field mask where the endpoint parameter structure is going to be populated with a peer address. This is that 231 byte object. And when standing up an endpoint, if you have a Ucx address, that is all you need. And so here calls into endpoint create, giving it the worker to associate with it, the parameters as specified above. And then we get a UCP endpoint handle that represents an endpoint to our server. Check status, and then from here, we go into our message code, where it just calculates how large our local address is, and then also gives it a size of the message structure. Now, this structure is just a 64-bit integer to specify the size of this address of this message. So after that, we actually allocate the message, check return types, set the message, and then we allocate, then we set the length in our message structure, copy the local address because we want to send that to the server. And now we get into our tag send code. So here the send parameters have a op mask telling it that we will be using the callback field along with a user data field. So up above, there is a send handler set, and that send handler will be given this CTX data structure. This CTX data structure is defined above so that it has a int in it, and that's used to manage the send state. I will go over that later in the example, but the way that it works is that you give it the tag send, and so here's the endpoint it's being sent to, the message that was defined above with min copy and the message data length, the amount of data, the tag our program is using hard-coded at the top of the program, and the parameters structure. Now, this is where we handle the Ucp status pointer type, because it comes back as a request. And so here's the macro UCS pointer is error to first test, was there an error in our send? If yes, it goes down an error path. Otherwise, if it is a pointer, that means that we have gotten back a request. The Ucx, the machinery of this example is set up so that that context that we have set up has a completed bit, and it will wait until the callback has set that bit before and wait on that. And then afterwards, we clean up the request, we clean up the message. Now we wait for the reply from the server. And we do that in a loop where we probe for the tag coming back from the server. So the worker that we expect to see the message on, the tag we expect to see the mask for this tag, and the info tag we expect to see back. From here, we get into the Ucp Worker Progress Function. This is the function that's used to tell the Ucx library that it's okay to now go into a lot of the details in the lower level library to try and make progress in the runtime. And so in this example, if the tag comes back as null, meaning that we have not received anything, this progress will be used to push the library and see if that will make the tag available. And so this loop will pull until it finds a tag. From there, we go back to our message structure where the tag will tell us how large the message we have received will be. And so we allocate into that. And then we call into the receive function. Now, again, it's worth noting that you do a receive against the worker. And so you get the message size, the amount of data you expect to read, which we get from the tag info, type information, the tag to receive on, and a callback for the receive handler. And here we do the same request checks, where first we see if our request is actually an error. And if it is, we go through free and cleanup code. Otherwise, we simply tell it to wait on this request. And then once we get the request back, we clear the completed bit, release the message, announce that we have received our message. Then we copy the message out of the data structure and into just a char pointer. And then UCP test success, the string. And then we have finished our client code. Free the message, destroy the endpoint, return success. Here we get into the flush callback. I'll gloss over this for now, but you'll see much of the same structure as seen previously. Checking against request types, progressing until it's finished, and then returning. So now we go into running our server. Now, remember the client got the server's address over the TCP IP socket, while the server will be receiving the client's address structure through the tag mechanism. So here we go through a similar loop as above, where the worker progresses, you probe to see if there's any tags available, and if not, repeat the loop until you have a message available. Then we have a repeat of the client code, where you allocate the message structure, receive using the same handler callback and everything else. And then we get the request. Again, check for error, bail if it's a bad request, block until the receive callback has been called. And then from here, we then unpack the address structure so that the server can create its own endpoint to the client. So here again, the server stands up its endpoint, same parameters, same address, and user data. Create the endpoint, check for errors. And now we create the message we're going to send to the client. First, calculate the length, allocate the message, set up our message buffer, generate the test string, error checks, and now we go back to our old friend, the send parameters. So giving it a callback, giving it user data, setting up the structures, and then tag send. Check, see if the request is actually an error. And then if the send didn't complete inline, then it checks, makes sure that it's a request. Block until the send callback has been called, and then release the request. Now, remember, if you get back UCS OK, and thus it is not a pointer, then that callback will never be called. So there's nothing to wait on, and you can just skip all these ifs and go straight down to the flush code. And this was the code that I skipped over earlier. But this is needed because when it's completed inline here, that does not necessarily mean that the message has been delivered on the remote side. While this flush will ensure that the message has been delivered. After that, you free up the memory, tear down your endpoint, return success, and then your run test function has completed. I'll go ahead and go over the callbacks just that, because here we have the flush, you have to give it a callback, and so there's just an empty callback for it to use. And here we have a non-blocking flush, which sounds weird at first, but it makes sense when you want to be able to call into worker progress and do other smart things while the flush is ongoing. So here you call flush MBX. If it's not an error and it's not a pointer, you announce the success of the flush. If it's an error, you handle the error. And if it's a request, you busy loop on progress, checking to see whether or not it's been completed. And then once completed, free the request, and then announce the status of what the request gave you. Here you can see that's checking the status of it. And if it says in progress, you just loop over the worker progress function. And the send and receive callbacks up here, if you remember, we gave it user data, which will come in the form of this void pointer. And so here we cast that into our context structure, which has the completed bit. So here it just sets the completed bit to 1, same thing in the receive handler, so that then in wait, when it gets that context, it can just busy loop over that. Check, see if completed has been set, as in the handler functions above. If not, call progress and see if that caused any of these callbacks to be fired. Anyways, this is the initialization function that we saw in the first demo, where we told it that for the requests, we wanted it to have some user data, and in this case, it sets the completed bit to 0. So that is how you do a simple string transfer from between host memory in Ucx. And so that was the run tests function. And then from there, it goes into the rest of the code path shown in the first demo. So, any questions?
Thanks, Matt. I think yeah, so like I guess are there other examples that folks can look at for kind of basic stuff? I know there's a bunch of Ucx Pi ones. Can you think of, are there any other UCP examples that might be useful?
So there are more examples in the Ucx Git repository proper, including a more complicated version of this example. I stripped out a lot of optional features, such as the ability to, instead of busy looping, call into sleep functions to avoid that sort of busy pulling behavior. And so if you want more examples and more sophisticated examples, those are available in the Ucx master Git repository.
Okay, great. I'll post the link in the chat here. Does anyone have any other questions? Okay. If you do, obviously, feel free to speak up. I think right now we're at, well, it's 2 o'clock Eastern time, but 11 o'clock Pacific time. So I think we're going to take a short break.
I have one quick question.
Oh, yeah.
Are there any multi-host example, or sorry, more than 2 kind of host examples that you all are aware of?
So there's actually a more complicated example called the IO demo. It's based on the client-server connection establishment, and it simulates flows which are related mostly to storage-oriented applications, like reading or writing to remote blocks. And it can connect, for example, you could connect multiple clients to the same server, or connect one client to multiple servers, and so on. It's also It's under test apps IO demo.
Okay, thank you.
That's a great question. So I'll see. I think I just pasted the link to IO demo as well. Okay, so feel free to keep asking questions. We'll do a short break here, and we'll return. And when we come back, we're going to talk a little bit about accelerators. You know, kind of bindings, Python, Go, Java, and then Yossi and Oscar will talk about basically how would you use Ucx if you wanted to implement support with some programming language. So we'll talk about Openmpi and OpenStream respectively. And if we have time, we'll kind of discuss what you might be interested in using Ucx for, and any other questions that participants have. Okay, so I will put it the break slide here, and we'll take about a 10-minute break, maybe 5 or 10 minutes. Okay.
Looks good.
All right. So I'll go over this slide. We have basically one slide to talk about kind of accelerators, and then we'll talk about findings and some of the implementations in this last part of the tutorial. So the key thing that we mentioned previously and that we wanted to kind of reiterate is that Ucx was designed initially with this thought process of we need to include accelerators in that they typically do data transfer and also have performance and performance portability requirements. The way that Ucx handles this is it specifies that an accelerator is structured as a transport object. So just like an InfiniBand or Ethernet link might be considered a transport, we can consider a GPU endpoint to also be connected into that. So as we mentioned here, if you think about it, with the GPU and a CPU, you might transfer data between host and accelerator memory, and typically, it's not specific to host data transfer or GPU data transfer, but we really just want to incorporate that into the Ucx framework. And we had a question about this in the last session, basically asking if you create one of these Ucp mem objects, how does it interact with something that is CUDA enabled? If you go and look at the second example we have, it's very similar to the first example. The format for a lot of things that Matt set up are very similar, but it's using, for instance, CUDA malloc managed memory rather than standard malloc memory. Obviously, you can specify certain flags if you want to do something that is not kind of detected by the Ucp API, but we'll try to help you make some smart choices if you say compile Ucx and compile a program with CUDA or Rockwell support built in. All right. So then we have this second example. I'll see if I can copy the link here. I don't know if you want to briefly go through that. Oscar or Matt, I'm not sure if you want to kind of lead that. I'll copy over the link here.
Yes, so Matt is going to show the modified example, the hello world that is using GPU memory. I'm going to go over there.
All right. Take back control of the screen. So here, I am now in the, so going into the GPU example code. You can see here that it's set up similar to the previous one. And The difference is that instead of GCC, it uses NVCC. And so that will call into the CUDA code. You'll also notice that that the example runs in the exact same way. However, rather than going through all the code, I want to show you the diff between this UCP Hello World code and the previous example that I went into in detail. So, declared a function to wrap the CUDA calls and check for success there. Replace CUDA, replace memcopy and CUDA memcopy, malloc with CUDA malloc, free with CUDA free. Change how the test string is generated to copy it onto the accelerator so that the memory being transferred lives on the accelerator. Important to note that after generating it on the host memory, it then just releases that memory and it's not used anymore. More changes into CUDA malloc, CUDA memset. And here we get to the one and only difference in any of the UCX code, where in the send parameters for the UCX server, the attribute mask is extended to include a memory type, and it's given UCS memory type CUDA. After that, the send function isn't any different. The receive function is also not any different. These two lines of code are the only things that changed in the UCX portion.
I see where I think I added I may have added a typo in there, Matt. So I'll fix that for those of you who go to run this later.
We will continue to improve these examples. Yeah, so in the receive code path, all that's changed is that the receive buffer was allocated with CUDA. And then from here, UCX figures out how to load that into the accelerator. And so the rest of the UCX code path remains the same. I also wanted to mention that in the server code, when we specify the memory type, this is actually, in many cases, optional. Now, one of the benefits of using UCX that people have mentioned is the fact that the sends and receives are done in a way that UCX figures out the fiddly details about how to move the memory. So the developers can focus more on their algorithms and how best to manage and move memory without having to deal with all the little details about how to actually set up these transfers. You're not having to figure out your own VIPC buffers. So, anybody have any more questions or want to see anything else about how this works with CUDA?
as I'll say, I have one question, which I think is probably pretty straightforward. I assume if you did a Rockham version of this, it'd be very similar. You're really just changing the memory allocation and maybe the the optional memory type parameter here.
Yep, the rock malloc and the memory types. AMD is also active in developing UCX. And so they make sure that Rockham support is built in as well.
Okay, great.
Anybody else have questions, anything they wanted to see?
I guess if they do, they can ask in the chat or speak up. So I guess I'll take the screen back from you. Thank you, Matt. So both of those examples are, you should be able to pick up and test. So thanks to Matt for developing them. Basically, as you mentioned, there are existing versions of this. Thanks, Whit. Thank you for joining us. This is an aside. But basically, Matt simplified these from some of the tests and examples that are in the main Ucx repo. So obviously, you can go look at these. We try to do these to be a little bit simpler, and we'll try to contribute these back to the main Ucx examples. All right. So let me reshare the slides here. And I guess, Matt, do you want to briefly talk about the bindings?
Certainly. So in addition to the C language and the accompanying C++, bindings are being developed for other languages. Ucx Java in particular enjoys first-class support where the Java bindings are in the Ucx main repository. And so if you have the proper Java tools, you can just build those bindings and leverage Ucx from Java. Now, this is even being used in projects like Apache Spark, where in the Ucx GitHub page, there's also linked to another repository for Spark built on top of Ucx, so that your Spark clusters can leverage the Ucx technology for high-performance interconnects. Also merged recently is Ucx Go, bindings for the Google Go language to similarly use Ucx, currently under active development. Another Ucx binding is in Python, where the NVIDIA Rapids project has built a Ucx binding and put their Dask and Rapids ecosystem on top of that. You can see the Dask tree in its animation, and over here is the task stream profile, where before Ucx, these red bits represents the library stalling on data transfer. And after using Ucx, where after the initial setup phase, the performance improves dramatically. And so right now, those bindings live in a separate Git repository in the Rapids GitHub page. However, we are developing a subset of those bindings to upstream into the master Ucx repository. So Ucx doesn't have to be a C-only technology. You can use many of your favorite programming languages and tools with UCX.
Okay, excellent. Thank you, Matt. Yeah, and we have, like, I think we were working on an example. We didn't quite finish it today, but hopefully we'll add that at some point. So.
Yep. Yep. So yeah, so the next slide basically say code snippet taken from the Rapids AI repository that shows some of the high-level bindings that they have been developed for UCX, in particularly the UCP part. And here is basically showing basically a method to test a send and receive in NumPy. And you can see that, for example, many of the C APIs has been, we have created a binding in Python. You see the operations like UCP init, UCP create, listener, and basically UCI create endpoint and UCP get address, when you need to get the addresses for the worker to create the endpoints and so on. So one thing to mention that, yeah, this is the way they design it, and it's a very high level API, and they also added some extensions, basically a library called sync.io. Since most of these operations in UCX are asynchronous, basically they added basically an await operation to make sure that they complete it's a synchronization construct, so that they can ensure that things are they complete when this gets executed. And yes, and then they abstract things like send, client receive, in their abstractions in Python. However, there are also other examples that use in the repository that has bindings for lower level operations for the communication part of UCP. And yeah, this is just to give you this code snippet we extracted from one of the test cases that we're pointing there. And eventually, this is a great example of basically those bindings, and there are plans that that we will have official UCX bindings for Python in the repository. All right. If we go to the next slide. Yes. So the next portion of the tutorial is a little bit more advanced, but we're gonna talk about how different programming models like OpenMPI and OpenSHMEM have been using UCX. And the idea is just to give you a flavor on basically that, that we have a complete API and something very robust to implement any HPC languages, any HPC language, and Josie is going to be talking about the OpenMPI and then part and also the MPitch discussion, and I'm going to be discussing a little bit about the OpenSHMEM part. So, Josie.
Hi. So I'm going to present how we did the integration between UCX and OpenMPI, which is actually very similar to how it's integrated into other MPI libraries like MPitch, for example. So OpenMPI supports UCX starting 1.10 version, which is a pretty long time ago. And UCX is implemented as a high-level component, a PML, which is a point-to-point communication layer. It means that unlike some previous work that we did, there is almost no software layer between the MPI interface and the UCX itself. It's a very thin layer. basically all the MPI calls are translated almost directly to the calls to Ucx API. There are a few parameters. So there are a few parameters which you can use to configure this glue layer, which are OpenMPI MCA parameters. For example, we can specify the PML to use, which is Ucx, unless it's already would be selected by a higher priority. We can force using Ucx this way. Okay, next slide. Additional parameters we can set is a log level of the integration layer and manually change the priority. Other than that, we can use the Ucx Info Tool, which comes with a Ucx distribution, to look at all environment variables which Ucx exports. -F here means to print the full information, including a full documentation of all configuration parameters which Ucx can accept. And here we have a simple command line example where we force using the Ucx PML and also specify which network devices Ucx should use for communication. Well, in case we have multiple network interfaces or devices on the machine, we can use it to use just a specific one. And next slide. So as a reminder, so Ucx would usually select the best transport to use. And supported transports include all the Infiniment and Rdma transport, including accelerated verbs for devices which support it, shared memory in Gini. OpenMPI uses either full direct modex, which means we either exchange all the addresses up front, or we can create endpoints and exchange the data on demand, which is useful, especially on large scale. And Ucx would create an endpoint to connect the ranks. Next slide. So the brief overview of Ucx objects is that we have the context and the worker, and in OpenMPI we create a single context, a single worker. The context is taking care of all the memory management internally, and the worker is taking care of the transport objects. And in case of MPI, it's also holding the tag matching queue. And since in MPI, it would be easier and if we had a global matching queue. And so we have a single matching queue, which is on the Ucp worker. And the endpoint represents a connection to the remote worker. In OpenMPI terminology, the endpoint is attached to OMP proc structure. Next slide. In addition, we have Ucp memory in Archi, which is used mostly on the OpenSHMEM part, which is also part of OpenMPI, and Oscar will talk about it later. And we have the Ucp configuration object, which is also used in OpenMPI to initialize the context. Next. So if we look at overall software layers, we have the MPI application, which is using the OpenMPI, exporting the MPI interface. Below that, we have the PML, which is the glue layer between MPI interface and Ucx. And then we have the Ucx library, which is implementing the protocols and transports. And Ucx is using the driver and the hardware, while in some cases it's also using the hardware directly in order to actually drive the communications. Next slide. So when we initialize the MPI library by calling MPI init, internally it initializes all components, including Ucx. So it calls a PML Ucx open, which just reads the Ucp configuration, calls the Ucp initialization function, which creates the one and only Ucx context, and then just release the configuration. Next. So continue the initialization stage. After we created the context, we create a worker, also the single worker that we have. Then at this point, we try to see what is the thread mode which was initialized with OpenMPI. So depending on what the user passed to MPI init or MPI init thread, and if the user passed a multi-thread request for support, and this Ucp worker would also be created with a multi-threaded mode. After we created the worker, we want to get its address and distribute it to all of the other ranks. So we call the Ucp Worker Get Address API, and then we publish it on the MODEX. And then again, depending on how we configure OpenMPI, we can either pull the address to the other ranks immediately, or it would be done on demand. And then we call just to the function to release this address. Next. In addition, in order to make progress on the communications, we need to add the Ucx Progress Function, which is a Ucp Worker Progress, to the list of all the callbacks for progress which OpenMPI holds. And this is done by calling Opal Progress Register. So after it's being done, whenever user calls MPI wait or anything like that, it would call all OpenMPI progress functions, which will also include the Ucx. Next. So after we initialize our context and register our progress, we can go ahead and send something. So for example, in case of non-blocking send, the MPI iSend is translating immediately to PML Ucx iSend. And then if we didn't create the endpoint yet, because for example, we use the indirect MODEX, then we create it. And after we created it for the first time, by fetching the remote worker address and then passing it directly to Ucp we create, we can call communication operations on that endpoint. So the MPI iSend would translate to Ucp tagsend NB, and in recent version, it would translate to Ucp tagsend NBX. And then internally, Ucx would decide, according to the size of the message, which type of transfer to use. So short messages would use a short, which means it actually means a different thing for different transports. In case of RDMA or hardware-driven transport, it usually means like post all the data to the PCI immediately and use Blue Flame. For things like shared memory, it means use a fastbox or put the data directly into the remote process memory. And if the message size is larger or the transport does not support it, we would use a bcopy mode, which means to allocate a bounce buffer from some memory pool, copy data to that buffer, and then post it to the network. Well, it has some advantage over zero copy that we don't need to register. We don't need to wait for a remote acknowledgement. We can just go ahead and send it. And if the message size is larger, usually we would use a zero copy, which means that we make the effort to register the memory in hopes that it would save us the time to copy the data. And the exact thresholds between short, bcopy, and zcopy are all decided and initialized when the endpoint is created. And it's according to the transport bandwidth, the estimated memory copy bandwidth, and so on. So, next slide. So then after we call this function, we can have several options here. So either the request completed immediately, and if this really happens, then we just return some dummy globally completed request to the user. So no memory pool allocation has to be done. So it's much faster. And if the request is not completed immediately, it would be progressed as part of all the OpenMPI progress callbacks. And then we just have to wait until it's completed. It's done by a callback function. So OpenMPI installs its own callback functions into the Ucx request when it's being sent. And then the callback function is eventually going to be invoked. This callback would mark this request as completed from OpenMPI perspective. So OpenMPI has this status object, which has to be updated. And then when the user calls test, wait, or test any or anything like that on the request, this function will return and the request would be considered completed. In addition, this glue layer supports contiguous and non-contiguous data types. So contiguous is pretty straightforward. We just look at the size of each data type, multiply by count, and pass the total size to Ucx. In case of non-contiguous type, Ucx has an option to specify pack and unpack callbacks, which would be used really when we have to pack and unpack the data to the transport buffers. So this is implemented by calling the Opal converter functions, which is a generic infrastructure in OpenMPI to pack and unpack or convert between different types. Next slide. So after we send the message, the other side can do receive, or even before that. So MPI non-blocking receive would be translated to this PML function, which would call a UCP tag receive. UCP will handle internally all the matching and the unexpected versus expected, and so on. There is some conversion logic of the tag. So in MPI, we have wildcards for the sender rank or the tag itself. In Ucx, we have tag and tag mask. So we pack everything into a 64-bit value. We calculate the mask, which would be different, for example, if we have a wildcard, and then post it to Ucx. And then Ucx could use, for example, either Eager or Rendezvous protocol to finally complete the data transfer. The sender would decide on it based on the data size. And if the data is small, it would use Eager. The receiver would get the message and copy it to the final receive buffer. In case of hardware tag matching, the data would be immediately available in the receive buffer. In case of a Rendezvous, the receiver would continue the Rendezvous protocol. There are several options here. It could be either based on Rdma read or Rdma write, or something more complicated, for example, pipeline protocols for GPU memory and so on. Next slide. So internally, Ucx could, as I mentioned, has all the queues, the expected and unexpected. We have some hash table for the tag, so different ranks or different communicators. In most cases, could have a shorter lookup in the queue. In addition, we could probe there is an API to probe for messages like MPI probe, and there are also special function tag MSG receive, which is used for MPI, mprobe, and mreceive as API. And the same as for send operations, if the receive isn't completed immediately, for example, it wasn't unexpected, so we just progress all communication, and the callback would be invoked when it's completed. Next slide. So the progress function would just call UCP progress. By the way, in Ucx, all the callbacks, no matter where they are installed, could be called only in the context of UCP progress. So send function or receive function will never call callbacks directly. And when the send receiver is finished, these are the callbacks in the glue layer which are being invoked. So it's called the MPI send or receive completion. And finally, when we want to shut everything down, we call MPI finalize, which internally calls OMP finalize, which in turn does a few things. First, it deletes all the processes, which is called the del procs. And inside our Ucx implementation, we implemented by calling UCP destroy on all the endpoints that we had. Next slide. And then we have a barrier, and we destroy the worker, and then we destroy the context. The worker is destroyed by a UCP worker destroy, and the context is being destroyed by UCP cleanup. But obviously, first we have to register the progress to avoid accessing invalid objects. Okay. Any questions?
No, there are no questions. I'm going to talk about the OpenMem integration with Ucx. Go to the next slide. Yeah, so OpenMem is a big-ass library that focuses on one-sided communication and has atomic operations and collectives, and maps really well to Rdma architectures for leverage that technology very well. And next slide. Yes, so the way it works is that we have processing elements, instances of those processes that share an address space called a symmetric heap or symmetric memory. And that symmetric heap is allocated at the beginning. All the processes allocate them in a collective operation. And then the heap size of the symmetric heap can be allocated with a variable. And then all of the symmetric data objects can be allocated, are allocated through shmem-malloc in that symmetric heap. And basically, all of these data objects are accessible by remote PEs. So symmetric memory, it includes, yes, dynamic allocated memory through shmem-malloc, which is also a collective operation. And then we have another type of symmetric memory, which is global objects and static variables of a program. Go to the next slide. All of those variables basically are remotely accessible by the PEs. So one of the properties in here is that we call them symmetric variables because the layouts are identical in all of the processes. And whenever we have these allocations and in symmetric memory or basically access the global section of the code or the static section, the layout and offsets are identical. So if we go to the next slide, this just very briefly shows the architecture of the OpenSHMEM reference implementation, which can be downloaded from the openshmem.org organization. And basically shows how the library is organized with the core components, and there is a layer called comps that is implemented with Ucx, and also they have a GasNet backend, but here we're going to focus on the Ucx implementation. For that, and it's meant to be a reference implementation so that people can see how easily programming model like OpenSHMEM can be implemented with Ucx. Next slide. So what happens, in SHMEM, we have a function called SHMEM init, which contains other initialization function at the comps layer, the comps init, and that's where we create the config, the UCP config file, the init. We create the workers. We initialize the memory regions, which we'll talk later, and then we create the endpoints for each PE. And basically, we do the release for the UCP config release. Next slide. So in OpenSHMEM, we basically, in addition to the symmetric heap, we have also in the object itself, we have sections that basically the data and the BSS segment in the object files that are basically global data. And all of those basically are accessible by the remote PEs. And as a result, we need to register them into the UCP context. And we use the UCP map to do that. And as we saw previously in the tutorial, that UCP memh will have a handle to access those segments. Next slide. And so basically translating the symmetric addresses. So we need to figure out basically what are the symmetric addresses in the remote PEs and to do the RMA operations. And for that, UCP needs the remote memory handle, basically to access, that's the key or the remote key. And to do that, first it needs to query where basically that symmetric object is, basically which segment, global, symmetric, querying the symmetric heap and so on. And then using that, once I locate where that is locally, then I need to translate basically that address into the remote buffer address. And since everything is identically in all of the processes, all of the PEs, basically it's easy to calculate through offsets. Next slide. And then here, very briefly, we just show how implement a put get atomic operation, which mem, where first we find the segment basically for the symmetric memory that we're going to do the operation. Then we translate and also get the remote keys for that in the find segment part. And then we do a translation where we find what is the remote memory address. And depending on the type of operation, we can pick a UCP put or UCP get or UCP atomic operation and the size. And internally, the UCP will pick the right UCP call or the right transport and also the right algorithm to implement that depending on the message size, the operations, and if they're basically atomic operations and so on. Next slide. So here is a brief summary on how both we can compile Ucx and also how we can build it, and also how we can build and basically Openmpi with Ucx support. The same thing with OpenMem reference implementation, how we do that. And it's pretty straightforward, and that will give you an example of how these two are integrated with each other. Next slide. So, and with that, we kind of wrap up the content of the tutorial. We try to make everything super clear in the tutorial to have the most important concepts. And that's the reason why we focus a lot in the UCP API from Ucx, when we demonstrated the main objects and the APIs, and we demonstrated how we can use that with simple examples like hello world, and how we could use it with to exchange to do communications across host memory across and also between the host and the GPU memory. We cover how Ucx is integrated with multiple programming models and examples of MPI and OpenMem. But there are also other implementations that you can take a look, and some of them are open source that also use Ucx, like Dask, and the Ucx that is used through the Ucx Pi effort that's being supported. And we also have efforts like Blazing SQL, which is also another tool that is used that uses Ucx, the C API, and it's a very successful project. We also want to mention that yes, Ucx is meant to be used across different devices and transports and network cards, and it supports a variety of systems and technologies, and we add them as needed. And this is a great opportunity to do that. If you want to contribute to the project, you're welcome to do that or use them. And as I said, the goal is to provide a layer that is portable, but it's also performance portable to eliminate the complexity of underlying driver sort of implementations. And the bindings are very important, and the fact that we support accelerators or first-class citizens in the API is also very, very important, as in the context of heterogeneous architectures, large-scale systems, as well as edge computing. We're starting to see a lot of more heterogeneity, and Ucx has the capability to handle all of these different devices. And Python, I think, is also very, very important, as there's a lot of code written in Python, as well as Java and access basically to the Spark plugins is also very important, and focusing on the data analytics to serve the data analytics space in addition to the HPC space. With that, we just go to the next slide. And this is just again, the link for the websites and the mailing list. And we're going to be posting those slides, as Jeff mentioned. And then we have a fun slide at the end for those who can stay and ask questions. We're going to be staying here a little bit longer than 3 p.m. to answer questions. Go to the next slide. And this is a word art, the Ucx logo with the Ucx API, basically from the documentation, and you can see that yeah, it's a fun thing to do and to share. And with that, I leave that to ask questions. And I want to say first, thank you for the speakers, Jeff, Matt, Josie, and Gilad. Everybody did an awesome job in preparing this presentation, as well as we want to say thank you to the HOTI organizers and Pavel Shamis and others that also contributed material to this presentation. And with that, we open questions if people have, and maybe Jeff, you can wrap up with the questions.
Okay, great.